My name is Ashley Foreman. This is Lab 5. This lab is on Faraday's Law, which relates the time-varying magnetic field to a curly electric field, whose path integral around a closed path is not zero, but provides an EMF that can drive current. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnetic tube interaction computationally, and then compare the computational predictions with my observed data. And so these are the fundamental physics principles. So we have Faraday's law with Lenz's law, which is the negative sign here, magnetic flux, the magnetic force on a wire, the magnetic force on a dipole. This is like parallel. If it was perpendicular, that wouldn't be there. EMF induced by a moving dipole, EMF equals B field VL sine theta. Main results, this is the experimental data. This is using the video that we took, if it ever plays. But it was just like the trial. We just took 5 videos of it falling through the tube and recorded the amount of time it took. And then here's the computational model, which we put in all the same like experimental data, but it came out to like 7.823 seconds, which is really weird. Here's the initial conditions in the system and surroundings. So the mass of the bar magnet was 0.03 kilograms. The magnitude of the magnetic dipole moment from lab 3 was 2.3253. Length of the tube was 0.47 meters. Width of the tube was 0.018 meters. Inner radius of the tube was 0.015 meters. Average time of the physical experiment was 1.92 seconds. And the system is the bar magnet and the foil roll, and then the surroundings is Earth and everything else. And so here's the code. This is just the first part. We just entered our experimental data and then creating the bar movement, the bar magnet. We put in the mu, and then this is just all from lab 3 pretty much, just equations. And then this is the R magnitude. This is again all from lab 3. And then here's the distance and such. The numerator, you're taking like the B field and such and all the things. And then this is the force of gravity, G times the mass. Negative mg because it's down, that's how gravity works. You have the flux calculations. And this is just the B field of the rings. And so this sine theta is just for calculating cross product. And yeah, this is just the net force. It's the gravity force plus the magnetic force. Yeah, and so this is just the magnetic velocity. This just comes from like the initial equations, like position equations and velocity equations, derivatives of like Newton's second law. And here's the experiment versus the model. So the experiment, on average, you get 1.192 seconds to fall through the tube. And then in the model, you get 7.823 seconds, which is a really big difference. And so the model takes almost 7 times more time to fall through the tube. And this can be accounted for. And so to change this to make it more accurate, the model, we could add, including some sort of external magnetic fields that affect the tube, making this time go down, as is in the experiment. And so the sources of error could have been the magnet hitting the aluminum roll, an accurate measurement of the time it takes to fall, and external magnetic fields affecting the magnet in the aluminum roll. What if the resistivity of the conductor were reduced as close as possible to 0? How the dynamics of the falling magnet change? A lower conductive resistance increases the current, which increases the magnetic field, increasing the time to fall through the tube. What if holes or slots were cut into the tube? How does this affect the ring currents in your model? Holes or slots in the tube would lead to less current in the tube as it breaks up the tube, leading to less rings of current. And this would make the magnet fall through the tube faster. And that's my lab. Thank you for watching.